So welcome back guys. So this lecture is the second lecture of linear algebra, and now we are going to start with the main topics. So let us start with the lecture 2, and in this lecture we are going to see the definition of a set. Then we would move forward with the field, and preferably if we can we would go to the vector spaces. So let us start. So the basics is very simple, that we first define a set. So set is basically nothing, is a set of values, can be complex, can be real numbers, can be like integers, anything. But these are some specific values which in every value is called an element of a set, right? So this is a set, and we have some properties to define a set. The set, and the only property is that every element of a set has to be unique, and these are very simple properties. This is taught in like very lower grade classes. So but what's important now in the set is, suppose we have a set with values like alpha 1, alpha 2. These are individual values in a set. We have beta 1, beta 2, beta 3, right? So the thing is, there are some specific properties which do not belong to the set, but if they are like properly followed, then they may give you something. So the first property is, if alpha 1 and alpha 2 belongs to a set, so if, when we start with the properties, if alpha 1 plus alpha 2 equals to alpha 2 plus alpha 1, so this is called the commutative law. After this, we will be doing another property, that is, if alpha 1 plus alpha 2 plus alpha 3 equals to alpha 1 plus alpha 2 plus alpha 3, and this is the associative law. Then we have another property, that is, if alpha 1 into beta 1 plus beta 2 equals to alpha 1 beta 1 plus alpha 1 beta 2, so this is called the distributive property. Apart from that, we have a property which is the, for every alpha, so this is the sign of for every, so we write for every like this. So for every alpha there exists, this is a sign for there exist, so there exists a minus alpha such that alpha, so this is such that alpha plus minus alpha equals to 0. This is called as additive inverse. With this, we have another property, that is, for every alpha there exists a 1 by alpha such that alpha into 1 by alpha equals to 1. Now here there has confusion, like many students get, what if the value of alpha is 0? So we often actually consider that alpha here is non-zero, and we all sometimes we do write it like, for all alpha, that is alpha not equals to 0, there exists 1 by alpha. But again, when we write for all alpha there exists 1 by alpha, so if alpha is 0, then 1 by alpha does not exist, so we cannot write there exists 1 by alpha, that is 1 by 0. So by law this statement is also correct, and actually I find more sense in writing it in this way. So that's why I don't write for all alpha where alpha not equals to 0. Rather, we can just write for all alpha there exists 1 by alpha, because if alpha is 0, there does not exist anything which is like 1 by 0, and this is called the multiplicative inverse. And after that we have the last property, that is if alpha plus 0 equals to alpha and alpha into 1 equals to alpha. So this is called the additive identity and this is called the multiplicative identity. If the set S actually satisfies all the above properties, then it is known to be a field. And we would look to an example of field in the next video. This is all for this video. Thank you so much.